Welcome. In this lecture, we will discuss the casting fundamentals, and first we will discuss the heat transfer. And the major concept that we will cover in this lecture, so I will first talk about the casting fundamentals. What are the three basic fundamentals I will talk about, and then I will talk about the heat transfer in stationary metal mold casting, and then I will talk about the heat transfer in continuous casting also. So, fundamentals of casting, there are the three fundamental considerations that are there for solidification. So, we will discuss. One is called the heat transfer, because heat transfer basically gives you the rate of solidification, and there is the rate of evolution of the solidified shell with time, that basically gives you the heat transfer. And then segregation is very important, because impurity segregation take place during the solidification, as we all know, and how to measure this segregation, that is the quantification of this segregation, that we will discuss. That is what is the impurity consideration in the liquid, how it is evolved with the time as well as solidification, that we will discuss. That is that quantification we will give. And we will discuss how to, since we will develop the model, based on that we can know what are the parameters that influence the segregation and how to eliminate the segregation as much as possible. And then another important thing during the solidification is the morphology of the structure. There is the morphology development during solidification, that is what type of morphology, it is the planar or columnar dendritic, equiax-dendritic. So, how this transition take place and what are the parameters that are responsible, that we will also discuss. Now, let us come to the heat transfer during the metal mold casting. I will just directly coming to the metal mold casting, because most of the casting take place in the metal mold because of its higher conductivity. And in the foundry, people use the sand mold casting also. We are not discussing, because we are mainly concerned with the ingot casting as well as continuous casting that take place in metal mold only. So, first we will develop a model, a very simplified model, okay, in a metal mold casting, and assuming there is no temperature gradient in the liquid as well as solidified shell, a very simple heat transfer. Okay. So, this is the mold, and it is water cooled mold, and then you can find that temperature, there is no temperature gradient in the mold, there is a mold temperature is constant at T0, and in between you have a solidified shell, and here it is the liquid. Okay, this is the liquid, and there is a solidified shell, and here you have mold, and there is no temperature gradient in the liquid, that is liquid is completely mixed without any temperature gradient. In the solidified shell also there is no temperature gradient. Actually, there can be linear profile or parabolic profile here, because it is unlikely that is the temperature. This is the melting temperature, I can say this surface is the melting temperature, and this is the solid temperature. It is unlikely throughout the solidified shell the temperature will be Tm. Okay, it will be little higher and solid temperature will be little lower, but we have considered for the sake of simplicity, let us consider it is Tm, and also we are considering in the mold the temperature is constant at T0. Okay, that is okay, that is likely, because it is water cooled, and so these two actually maybe little some simplification is there. Anyway, to start with, to develop a model, we will do that. And here the Tp temperature is the liquid temperature, Tm is the melting temperature of the liquid, okay, T0 is the mold temperature, and m is the thickness of the solidified shell at time t, at certain time t. Now, heat transfer is limited by contact resistance at the mold casting interface. You can find I have tried to show a contact resistance. What is that contact resistance? A solidified shell and the metal mold, they will not be perfectly matching. Actually, we also do not want that they should perfectly match, or they should be welded together. Okay. So, otherwise the solidified shell will be welded with the metal mold casting. We also do not want, that is why people use some kind of lubrication such that the casting can be taken out after it is cast in the metal mold. So, some lubrication is there. So, and we also don't want a perfect contact between them such that they can be taken out. Okay, some lubricants are there. So as a result, when the steel shell solidify, when the liquid solidify over the mold wall, there are a lot of gas and gap, okay, asperities, gaps, gas pores, okay, all are there. That basically detach the casting from being molded with the metal mold. Okay, so we can consider that there is a contact resistance. There is a huge resistance will be there. Because of that, the heat transfer resistance will increase, because if there are some gas pockets at the interface, they will give the heat transfer resistance. So basically heat transfer is controlled by basically more, that's why we have considered this the linear profile. Some assumption is there, because this resistance is much more compared to this resistance. Okay, obviously there can be some resistance to heat transfer in the solidified shell we have not considered here. Here we have considered, if you consider a constant temperature in the solidified shell, you do not consider any resistance to heat transfer, that is infinite conductivity is there, that you are considering, but actually not. So all the resistance, so here basically this resistance is too high, then this type of assumption may be little bit justifiable. Okay, so because we are trying, that is the most of the resistance is lying in the interface. Okay, so that contact resistance is there. Now let's consider, so heat flux, that is the thing. If I consider that is the heat transfer is controlled by this resistance, then whatever the heat is generated during this solidification, so all the heat will be transferred through this contact resistance. Okay, so the heat flux that is generated during solidification, because of latent heat and the heat will be generated, because the liquid temperature will come down from Tp to Tm, that is the sensible heat. It will release amount of sensible heat from Tp to Tm, and then Tm to liquid at Tm to solid at Tm. So that much of latent heat also it will evolve during the solidification. So all this heat has to pass through this contact resistance. Okay, so and all other this resistance, there is no solidified, there is no resistance in the solidified shell, only resistance I am considering here. So we can easily calculate what is the flux that is going through the contact resistance and heat evolved. Now heat release per unit time by liquid at solidification rate. Let us consider the heat released per unit time first. Let us consider, that is during solidification how much heat is released per unit time. If you consider the solidification rate is V naught. V naught means that is the volume of liquid that gets solidified per unit time. So if I consider, then this is the thing, this is the amount of the volume of the liquid that is getting solidified into rho s, that will give you basically the volume of the metal, that is the mass per unit time. This is the mass per unit time, that is the metal that is getting solidified, mass per unit time, and then into delta HF latent heat, it is basically that is the calorie per unit mass. So this term V naught rho s into delta HF will give you the amount of heat released per unit time due to latent heat of fusion. Okay, and this is basically gives you the sensible heat, because V naught into rho L is the liquid density, because it is the liquid. So mass of the liquid per unit time that will get solidified into CPL into Tp minus Tm. This will give you the there is the heat released, there is a sensible heat released when the liquid temperature comes down from the pouring temperature to the melting temperature. So or you can take out now the common Vp rho s also out of it, and let us consider this rho L is equal to rho s, and in that case I can write in this form, V naught rho s outside, then delta HF plus CPL Tp minus Tf, and then V naught rho s into delta HF prime. Delta HF prime represent this term, that is this sensible heat as well as latent heat. Okay, so HF prime. So this is the total heat that will be released per unit time during solidification at a rate of V naught, that is the volume of liquid that is getting solidified per unit time. And heat extracted at the mold cell interface, that is the amount of heat that is extracted at the mold cell interface, is here we can invoke the concept of heat transfer coefficient. That is, the heat flux at any heterogeneous interface through a thermal boundary layer is basically given by H into delta T. H is the heat transfer coefficient, delta T is the temperature difference across the thermal boundary layer. So, here basically we can do that thing H into Tm minus T naught into A, where H is the heat transfer coefficient and Tm minus T naught is the temperature difference, Tm minus T naught, and H is the heat transfer coefficient, okay, in the thermal boundary layer. Okay. So, this is, so at the contact resistance, so H basically represents the heat conductance in the thermal boundary layer and Tm minus T naught temperature difference, I multiplied by area because this is the flux multiplied by area because heat per unit time. So, this will be the heat that will be extracted per unit time, okay, into the mold. So, if you just equate these two terms, keeping in mind that is V naught is equal to simply A into dm by dt. Dm by dt is basically rate of solidification, A is the area. So, if you do that, then you get, after doing some integration, simple integration 0 to 2 and 0 to m. So, m will be coming like this. So, you can simply get, that is the instantaneous thickness of the metal at any time t is given by H into Tm minus T naught by rho L delta Hf prime into T. Okay. So, this is the way you can calculate it. Okay. So, this is for metal mold, stationary metal mold casting, batch process like ingot casting, you can calculate this way. And if you use a linear profile, basically in the temperature, it is unlikely there is no resistance into the solidified shell. There will be a resistance because of conductivity, depending on the conductivity, and conductivity of steel is not that high that we cannot consider compared to this contact resistance. Okay. So, we cannot neglect this resistance completely. Okay. So, if you consider this resistance, we can consider a linear profile obviously, and then assuming that linear profile, you will have two resistance in series. One is the 1 by H at the contact resistance, another is in the solidified shell, the resistance will be m by k. If you just draw an elliptical analogy, then across T naught and Tm there are two resistances are coming. One is obviously contact resistance, and now H is the heat transfer coefficient, is the inverse of the contact resistance. So, contact resistance 1 by H. H basically gives you the heat conductance across the thermal boundary layer. 1 by H is the resistance across the thermal boundary layer. So, this is 1 by H here, and m by k, you can simply, it is easily to show that is m by k is the resistance in the solidified shell. So, modified heat extraction through with the combined load, that is the total, that is the resistance is 1 by H plus m by k, and Tm minus T naught is the potential difference into area. So, this is the flux, Tm minus T naught by resistance is the flux into area, there is the heat per unit time that you are extracting through into the mold. Okay. Now, two resistance are coming into picture. Now, you can equate it and then you can integrate it, that is this flux should be equated to, and there is the heat that is generated per unit time for due to solidification, and then you rearrange the terms and you can integrate, and after integrating you will get this equation. You get basically a parabolic, that is the quadratic equation, and then if you solve it you will get the mold thickness. So, you can see a little change, that is if you just include some more resistance into the solidified shell, the equation become complicated. Okay. That is why we took it simplified. Basically, if the resistance, contact resistance is too high, then you can neglect the resistance here. So, straight line assumption is not a bad assumption because your expression become much simpler. Here the expression is quadratic equation you have to solve. So, only for, so sometimes you have to understand that is the whether you will complicate the problem or not. You can make the problem as simple as possible, okay, if it permits. So, if 1 by H, for example, if this resistance is much higher compared to this, you can simply neglect this resistance, okay. And in this case, I think it is not a very great, it is not very wrong if you assume that it is a linear profile, okay. It is a constant temperature across the solidified shell anyway. Otherwise, it is little complication is coming, and based on that, if you see the value of m, it will not differ too much. Now, this in case of heat transfer in the continuous casting, this case is little different. In case of the continuous casting, you know, that is the metal is cast at a continuous rate, that is the metal is also moving. Okay, it is not that it is stationary, it is moving. I think I have a picture. So, it is the turn disc, from the turn disc the liquid is coming, and you can find in continuous casting what happens in the mold when the casting is moving at a constant speed, and when the casting is coming out of the mold, the skin thickness only grow. Okay, and inside there is liquid. So, the liquid does not become solidified when it comes out of the mold. It stays for a longer time, and then that is why you require a secondary cooling. When the casting come out of the mold, you have a secondary cooling such that the core liquid gets solidified. So, when the whole core liquid gets solidified here, that is called the metallurgical length. Okay. So, then that is the point at which all the core liquid is solidified, but when it is coming out, it is not. And also the casting is moving at a continuous speed. And this skin thickness, when it is coming out of the mold, this thickness should be sufficient such that under the action of the fluid pressure inside, it does not come out. Liquid does not come out by breaking the skin. Skin should be sufficiently thick. Okay. So, anyway, that is another thing, but here what I am telling is that the casting is moving in a constant velocity in this direction. So, you have another heat transfer component because of convection. If you just, your stationary observer, you are looking at certain section into the mold, and then in that case you can find that a material is coming into the mold and going out. So, a material is coming and going out. So, there is a convection. Okay. So, from that point of view, it is not a batch process as we have developed. So, that equation will not be valid. That is the that we have developed in the first slide, that is, that equation is not valid. Even in previous slide whatever developed is not valid, because that is for a batch process where the casting is not moving. In this case, casting is moving. As it is moving, we are contributing some convection heat transfer is also will be contributing, that we have to consider. So, and also if you see the temperature profile will not be that simpler. You can see the liquid is here, and then there is a gradient, this type of concentration. There is the temperature bound, thermal boundary layer will be like this. Okay, here is also like this. And also the temperature profile in the solid, you can find in the solid region also there is a parabolic temperature profile. This is also parabolic temperature profile. We have given these two temperature profile at two distance, axial distance, because the liquid is coming. And also you can find that the shell thickness is not constant across the axial length. If you see axial length, shell thickness is increasing. That is, the aim is a function of, if you tell y is a function of y, that is a function of axial distance or y, and is the horizontal distance I have represented by the x. Okay. So, and at two different axial location, at y prime and y double prime, we have shown you two different temperature profile. Actual temperature profile is parabolic because of convection that is coming into picture in the solidified shell. So, we have this is the governing equation. The governing equation, we can find two component. One is in the y direction, we have a predominant convective term is there. This is the convective term. And the x direction heat transfer is mainly by the conduction. There is no convective term. So, this is the heat transfer, and it is basically steady state heat transfer in this case. That is with respect to a stationary observer. If you just make an heat balance in a constant, a fixed control volume, and you will find that certain amount of heat is coming into the control volume and going out in the y direction, x direction heat is diffusing, and then you will get this type of equation. And is basically a steady 2D heat transfer with convection in the y and conduction in the x. And initial condition, what are the initial condition? You can find that at y is equal to 0 at the wall, that is at the mold wall, okay, for all x, that is for all x, at y is equal to 0 means here, there is all x here. At this temperature, the liquid at the pouring temperature, or T is equal to Tp. Across this line, everywhere liquid temperature is the liquid temperature or the pouring temperature, T is equal to Tp. And boundary condition that is basically initial condition is for basically at y is equal to 0 for all x. Okay. And boundary condition, you can see there are two boundary at x is equal to 0 and at x is equal to mx, my. My means that is this across this thickness, solidified shell thickness here. This is one boundary, this is another boundary. Here x is equal to 0, here x is equal to my, m as a function of y, right. So, at x is equal to 0, what happens here, whatever the heat is coming by conduction in the reverse x direction, that is why it is k dt dx, it is not minus k dt dx because heat is moving in the negative x direction, okay. So, k dt dx here, whatever the heat is coming to the mold solidified shell interface is equal to the heat that is extracted by the mold across the contact resistance, okay. So, H into Ts minus T naught. Ts is the solid temperature here, Ts minus T naught and k dt dx, okay. And another boundary condition at x is equal to mx for all y. And one is you can find that at x is equal to mx, T is equal to Tm, because across this thickness temperature is the melting temperature. You have another boundary condition at this same boundary, that is the whatever the heat that is going inside the solid by conduction, that is the kx dt dx, is equal to, that is the heat that is developed during solidification, that is released during solidification, that is rho L HFU dm dx. You can write like this also, because I am incorporating u is the velocity, okay. So, basically velocity and it is dm and it is dx, okay. So, it is converted. So, you can get that thing, that is the whatever the heat that is developed per unit time should be going into it, okay. Basically, here the time be dm dt has been converted by your dx by u, dt is converted by dx by u, because you can simply convert the time to the distance, okay. dt is equal to dx by u. So, that conversion has been taken place. So, you have this thing, and if you can solve this equation, this is an analytical solution is possible, a simple analytical solution is possible, and this is given in the form of a graphical form. You know, it is not very, I will not say this solution numerically is very easy, but analytically this solution is not very easy, but it is available now, and results are available in the form of a graphs. So, these are some of the graphs where you can have the solution in the graphical form and dimensionless number. So, in this plot there are several such plots are there. In this plot, what is plotted? In the x axis you have basically dimensionless axial distance. You can call it dimensionless axial distance. It is defined as h square y by u, ks, rho s and cps, okay, where h is heat transfer coefficient in the thermal boundary layer across the solid liquid interface, and at the heat transfer coefficient at the solidified shell mold interface, okay. And y is the axial distance, u is the velocity of the casting, ks is the conductivity of the solid, rho s is the that is the density of the solid, cps is the density of the heat capacity of the solid, okay. And these basically represent dimensionless solidified shell thickness at an axial distance y, where h is the heat transfer coefficient, my is the shell thickness at axial distance y, ks is the solid thermal conductivity of the solid, okay. And this is also, this term, this is also dimensionless, you can say dimensionless latent heat of fusion, okay. And it also considers the sensible heat, that is that you know delta H F prime, okay. So, delta H F prime we know by definition what is that, is latent heat plus sensible heat, that part. So, this is the delta H prime, it is normalized by CPS, that is the heat capacity of the solid, into Tm minus T naught, melting temperature, mold temperature. So, this is also a dimensionless latent heat of fusion, you can say. Now, in this case you can see for a, if I ask you to calculate the solidified shell thickness at a distance y, so you know the value of y. So, now all other parameters are known to you, you can calculate the dimensionless y. At the dimensionless y, suppose it is 0.4, you now go move up, and then you see what is this value. This value you can simply calculate depending on the material. You know latent heat of fusion is constant, and also you know how much superheat, and then you know this CPS, everything is known to you. So if you know the value for the metal being cast, here liquid steel is being cast. So if it is say 0.3 I am considering, okay, my case, that is this value is 0.3, dimensionless latent is 0.3, dimensionless distance is 0.4. So I move like this and here, and then from here I will go like this. So this will give you the dimensionless shell thickness. Okay. Now if I want to calculate the shell thickness at the exit of the mold, which is most important, that is called the skin thickness, that is called the skin thickness. Okay. And skin thickness is very important. As I said, it should have, when the casting is coming out of the mold, it should have sufficient thickness such that it can withstand the internal liquid pressure, because liquid is there inside and it is a huge pressure, so it will try to break the skin. So skin should have sufficient thickness such that it can withstand that pressure. So that's why the skin thickness at the exit is very important. Okay. So skin thickness at the exit is very important, and so then at the exit, what is the value of y? Value of y at the exit is simply the mold length. So you can simply do that. So it is the dimensionless. So if you put y is equal to capital L, so you will get the dimensionless distance of the mold length, and if you know there is the dimensionless latent heat, so you can come here and then plot it, and then you can get the dimensionless shell thickness at the exit of the mold. Okay. And from the dimensionless shell thickness, you can simply calculate the my, that is the ml, that is the thickness, skin thickness, just by multiplying by ks by h. Okay. So that is the way you can calculate the shell thickness, and it will be a much more accurate compared to the previous techniques, because there we don't consider the casting, movement of the casting. Okay. So this is the way, this is for one graphical representation. Similarly, some other graphical representation there. For example, if you want to calculate what will be the volumetric flow rate of the liquid in the mold, that will give sufficient heat extraction from the mold. Okay. So those graphs are also available. So this is the way you can, this much heat transfer basically I want to consider in this case, and your reference is basically Geiger and Fourier, transport phenomena in material processing. This is a very good in transport phenomena, you can consult this book. Okay. Now conclusions. So basically the three fundamental considerations in solidifications, basically as we have discussed, are heat transfer, segregation and solidification morphology, and in this lecture I have covered only the heat transfer. And solidified shell thickness during solidification under simplified temperature profile, that is without any temperature gradient in the liquid solidified shell and the mold, may be given as this. So this formula, that is you can use for metal mold, that is for a batch casting process like ingot casting. So if you want to do ingot casting, then if you want to calculate how much time the liquid steel will take for casting. Okay, so how much time is required, you can use this formula. So you can know, you know the evolution of the shell thickness, so you can note for complete solidification time, how much time is required. Okay. Basically, if you are casting in a cylinder, so in that case m will be basically the radius. So if you attain the radius, because from both end casting will come. So if you cover, when the m become AR, then your casting is complete. So what is the corresponding time? So that you can calculate for metal mold casting, that is metal mold ingot casting. But for continuous casting, as I said, since there is an casting speed is associated with it, so you have to consider a more rigorous solution, analytical solution based on differential equation and boundary condition that we have discussed. Okay. So those solutions are available in literature. You have some graphical solutions, so you can use those, okay, to calculate the exit skin thickness and all these things. In spite of this thing, and in this solution that I have provided, in the graphical solution also, it doesn't consider the temperature gradient into the liquid. Okay, it considers that the liquid is completely mixed. Okay, so if you make a complete CFD, then possibly you will get a much more accurate result, because it is unlikely that is the liquid steel into the mold is completely mixed. Okay, so that thing also not considered into the graphical solution. Okay, so that thing you should keep in mind. But anyway, so we have given some improved models such that you can calculate more accurately, but the accuracy do not end there. So if you can go for CFD, you can complete that is the temperature history into the liquid steel also inside the mold, then you will get a much more appropriate expression. Besides, you have the mold wall, there is the heat transfer coefficient H. H also is unlikely to be constant across the wall, across the axial distance they can vary, because it is very difficult to maintain a constant heat transfer coefficient across the wall because of mold flux distribution is not very uniform across the axial distance. So those problems are also there, but we have assumed a constant heat transfer coefficient at the wall. Okay, so these things you must keep in mind, but if you can calculate the shell thickness from this, it will be much more, because if you make a much more accurate calculation, the shell thickness is not going to change very significantly. So as a first hand knowledge, there is the what should be the scale thickness such that the bleeding does not occur, liquid metal does not come out. These formulas are much more good, that is sufficient. So with this I come to the end of this conclusion. Thank you very much.